Okay, folks, it is that time of the day, so I am going to go ahead and get started. Some announcements. I posted homework number 2 today. It's due Sunday, September the 11th by 11:59 p.m. I'm going to start very, very briefly, I hope, with a recap, because the things that we have been discussing are directly related to what we will be discussing today. So we started the semester talking about the arrangement of the periodic table, and while all of the arrangements have their value, the ones that we will be working with today include the groups and the periods. As a reminder, the groups are the columns, the periods are the rows. We will also talk about the main group, group 1 and 2, and groups 13 through 18. We'll talk about the transition metals, which are groups 3 through 12, and then the Lanthanide Actinides, which are the ones on the very bottom of the periodic table. Then on Wednesday of last week, I can't keep up with my days and times at this point already. We started talking about the atoms of the elements. Atoms of elements have 3 subatomic particles. They have the protons. The protons are responsible for the element's identity. The protons are a constant. They are always the same for every single atom of that element. The protons are represented by the atomic number, which is the blue number on the periodic table at the top of each box. We talked about the fact that also inside the nucleus are neutrons. That's supposed to be neutrons are inside the nucleus, and the neutrons are responsible for an element's isotope. The only reason different atoms of the same element can have different masses is because they have different numbers of neutrons within the nucleus. And then finally, we talked about the electrons. The electrons are found in the electron cloud surrounding the nucleus of the atom, and the electrons are responsible for an element's reactivity. Now, today, what we're going to do is we're going to start by talking about average atomic mass. If you will recall, when we were talking about the atomic number, the mass number, the protons, the neutrons, the electrons, I asked how many of you had been told that the mass number was on the periodic table, and many of you raised your hands. What is actually on the periodic table in red at the bottom of each box on the one that's on the wall is the average atomic mass. The average atomic mass takes into account all naturally occurring isotopes and their abundances. So the number at the bottom of each square on the periodic table is not the mass number. Mass numbers are whole numbers. What that number is the average atomic mass, which is related to all of the isotopes of that element. The second thing we're going to talk about today is going to be the electron configurations. As we talk about an electron configuration, what we're going to be doing is helping you to identify where every single electron within an atom resides. Now, this particular talking about the electron configuration gives us insight into so many different things about an atom of an element. Number one, it describes how element number 87, which is francium, is so much more reactive than element number 3, which is lithium. The electron configuration helps us to understand why. The electron configuration helps us to understand why Group 1 elements always form a +1 cation, which we'll talk about more later. And why group 17 halogens always form a -1 anion. It all has to do with their electron configurations. So the understanding the electron configurations can greatly help you to understand more about the periodic table. It can help you to understand why certain elements will form what are called ionic compounds, while others want to form covalent molecules. It all has to come down to their electron configurations. So let's begin with the average atomic mass. You can calculate that number at the bottom of each square on the periodic table. That number is going to be equal to the sum over all naturally occurring isotopes of the isotope's mass times their abundance. When you look at this formula, folks, the isotope mass is the result of the mass of the protons in the nucleus added together, the mass of the electrons in the electron cloud added together, and the mass of the neutrons added together. So each one of those subatomic particles, if you will recall, had a mass. In order, they do not lose mass. So that means that if you have hydrogen, which has 1 proton and 1 electron, then you would expect hydrogen's mass to have the mass of a proton plus the mass of an electron, because each one has a mass. Now the abundance. Abundances are determined using instrumentation. One type of instrumentation is called a mass spectrometer, which basically will separate out substances based on their masses. And it will give us an idea of how much of each component is present. Now, folks, you are not going to be able to you're not going to be able to calculate the isotope mass. We could come close, but we're not going to get it exactly correct. You're not going to be able to calculate the isotope mass. And you're not going to know the abundances unless you have an eidetic memory and have looked at a table of naturally occurring isotopes. So all of that data, the isotope mass and the abundances for each isotope will have to be given to you. So an example would be the fact that nitrogen has 2 naturally occurring isotopes. Those 2 isotopes that are naturally occurring are nitrogen 14 with its 7 protons and 7 neutrons, and nitrogen 15 with its 7 protons and 8 neutrons. Now, nitrogen 14, if we determine the mass of the material, has a mass of 14.00307 atomic mass units. That's what AMU stands for, is atomic mass unit. And nitrogen 15 has a mass of 15.00011 atomic mass units. Now, if I were to go dig up a sample of nitrogen the sample is the whole. It would be considered 100%. Now, if I were to analyze that sample of nitrogen, 99 plus percentage would be nitrogen 14, meaning 99%, over 99% of the atoms of nitrogen in that sample are going to have 7 protons and 7 neutrons. 0.36% have the 7 protons and 8 neutrons. Now, we apply our formula to this calculation. To get the average atomic mass, it is going to be equal to the mass of the first one times its abundance. Now, here is something you need to note. What I gave you was percent abundance. So you're going to need to take that out of percentages and make it abundance. So that's 0.9964 and 0.0036. You got to take it out of percentages and make it just abundance. So 14, no ma'am. No.
You're not.
No. Lay down. Leave it. Okay. We're going to take that 14.00307 atomic mass units. We're going to multiply it by 0.9964. To that, we are going to add the 15.00011 atomic mass units times 0.0036. When you complete that math, what you get is 14.00665 AMUs. And if you look at the periodic table up there on the wall, you will see that it reads 14.00674. 00674. Considering how far into the decimal places this number is, if you'll notice, they both round to 14.007 basically. This is how those numbers at the bottom of the periodic table were determined. Now, folks, I will warn you, this isn't exact. Depending upon which table I get my atomic mass unit for each isotope determines the exact calculation, but you're going to get pretty darn close to what's over there. Let's look at another example. Silicon has 3 naturally occurring isotopes. The three naturally occurring isotopes are silicon-28, silicon-29, and silicon-30. First thing I'm going to do is take my percent abundances out of percentage and just get them into abundance. Now I'm going to apply my formula. The average atomic mass is going to be equal to 27.97693 for silicon-28 times 0.9223 plus 28.97649 times 0.0467 for silicon-29 plus 29.97376 times 0.0310 for silicon-30. I know it's hard to read in the back because the numbers got closed, but basically all I did was take each mass and multiply it by its abundance. And now I'm ready to complete this calculation. And I got 28.086 AMUs once I round to like 3 significant digits. And silicon, if you look at it, is going to be right around the 28.06 something mark. So again, protons tell you the identity of the element. Neutrons tell you the isotope of the element. Electrons determine the element's reactivity. The atomic number, which is found on the periodic table, is equal to the number of protons, and in the case of a neutral atom, is equal to the number of electrons. But you cannot find the number of neutrons on the periodic table. The only way to determine the number of neutrons is by knowing what isotope you're working with. The mass number, which is the number of protons plus the number of neutrons, is not on the periodic table. The only way to get the mass number is to do some mass spectrometry to actually determine what the mass of the isotope is. What's on the periodic table is the average atomic mass, which takes into account all naturally occurring isotopes. Questions about average atomic mass? Yes. I will be asking you to calculate the average atomic mass, yes. And calculators are necessary on test days. Okay. So now what we're going to do is we're going to move into electron configurations. The electrons are responsible for an element's reactivity. Understanding where every single electron is located in the atom helps us to understand an element's behavior. Now, I'm not going to get into all of the science associated with the electron configuration. As you progress into college chemistry 1, if you take that subject, you'll go into more detail. And if you decide you like chemistry and take a lot of chemistry and take physical chemistry, you'll go into even more detail. What I'm going to do is take all of the science that led us to understand the electron configuration and just boil it down into the bare basics. Basically, our understanding of the electron configuration was the result of a mathematical model developed by Schrodinger. And this mathematical model, once it is used, produces what are called quantum numbers. So basically, I do a bunch of math and I get out these quantum numbers. And when I say a bunch of math, I'm talking calculus, specifically integrals. It's multiple integrals and takes forever to do for just hydrogen, which is the smallest atom up there. So, but anyhow, this mathematical model produced these quantum numbers. And by using these quantum numbers, we have an idea of where the electrons are located. Now, I am not going to get into all 4 quantum numbers. I'm only going to get into 2. We will focus on the first 2. First number is known as the physical quantum number, and the second one we'll talk about is the angular momentum quantum number. And it is at this point that I decided to start writing so that I slow down just a little bit. The principal quantum number is a whole number. It is going to be 1, 2, 3, and so on and so forth. The principal quantum number is related to the period number of an element. The principal quantum number describes how far away from the nucleus an electron resides. The larger the N value, the further from the nucleus does the electron reside? Now that particular piece is important because the further from the nucleus an electron resides, the more reactive the atom of the element will be. So, and I think I gave you this example because it's one of my favorites, the alkaline metals. Lithium number 3, you throw it in a tub of water, it's just going to zing around. It's not very reactive. As you went to sodium, as it zinged around, it caught into. As you went to potassium, which is below that, as it zinged around, it went into a sparkler type effect. Rubidium blew a hole in the tub, and cesium blew the tub into pieces. That's because as we went down that period, the outermost electron was getting further and further and further away from the nucleus. And so it was more reactive. Now, the angular momentum quantum number, angular which is represented by an L. Describes the subshells shape where the electron can be found. Now, I could give you the numerical value, but we also have a letter notation associated with angular momentum quantum numbers. The letter notation if my screen can catch up. The first one is called the S subshell, and it is spherical in shape. And basically, our nucleus sits at the center of that sphere. I know it's very difficult to see. And again, I told you I can't draw worth flip. These are two examples of an S subshell. They're just little balls, nothing major. And at the center of these little balls would be our nucleus. The second letter notation is that of the P subshell. And it is dumbbell in shape. Or you can think of it as two balloons attached at the center. In this particular case, the nucleus sits right there where the two dumbbells come together. And I'll pass all these around in a minute. This is a P. It has two lobes. The third one that is called a D subshell, and it is cloverleaf in shape. Again, that nucleus sits right in the center. It's always in the center. This is an example of a D subshell. Now, I'm not going to go into the quantum number that tells us this. If you want to know, you can come see me and I'll tell you. But when we have the S subshell, we have what is called one orbital. Or in other words, it's just one sphere. When we have the P subshell, we have three orbitals. And I've drawn one of them. There would be another that goes on this axis and then one that goes away from you on the axis. So there's three of them. One that's on this axis, one that's coming towards you and away from you, and then one that's standing on its edge. So every which way you could turn this, that's how you would figure it out. And with the D subshell, there are 5. Orbitals. Now, why is the number of orbitals important? Because the maximum number of electrons per orbital is 2. So going back to what I was working with earlier with this new piece of information, if I only have one orbital, then my max electrons is equal to 2. If I have 3 orbitals, then the max electron is equal to 6 because each orbital can have 2. 2 times 3 is 6. And if I have the D, the max subshell, which has 5 orbitals, the max would be 10. Questions? I know right now I'm just throwing information at you. We're going to develop the Electron Configuration shortly, I hope. Because there is a 4th quantum number called the spin. And one will spin left and one will spin right. And those are the only 2 ways it can spin. So that's why it can only hold 2. Other questions? Okay, so folks, all of this information is embedded right there in that periodic table. All of this information is embedded right there. So let me do a quick jot of the periodic table real quick. Okay. Okay, so there's our periodic table. What did I say N referred to? The what? Principal quantum number. It's a little bit different, so I'm being very careful in this. So this group, basically, your alkali metals and your alkaline earth metals are the NS, where in this N equals X, and X, when I refer to X, I'm referring to the period numbers. So let's talk about it. In this particular case, the period number equals the principal quantum number, which was the letter N. So if you look at lithium and you look at beryllium, they are in 2s, meaning they are in the second layer away from the nucleus in an S subshell, which is the spherical subshell. By the way, for this purposes, even though it does not appear that way on the periodic table, for this purposes, helium goes with the 1s. Now, when you get over to the other part of the main group, which includes all the way over to the, from group 13 to group 18. This is referred to as the NP. Where N equals the X again. In other words, it's equal to the period number. So if you are talking about boron all the way through neon, their last electron is going to be in the 2p's. Yeah, this is why you got so many blank periodic tables early on. You need to draw it in there. Now, this intersection, your transition metals. Your transition metals are the ND, but in this particular case, it is equal to X minus 1. So if you're looking at scandium over to zinc, they are in period 4. So they would be in the 4 minus 1, or in other words, they're in the 3D. Their last electron is in the 3D subshell. Okay, so there is a rule that is related to the energy of each of our shells and subshells, or each of those principal quantum numbers compared to the shell. And it just so happens that these 3Ds are just a hair fraction, and I do mean a hair fraction, higher in energy than the 4s. And because they're that hair fraction higher in energy than the 4s, they come just a little bit later on. But they're called the 3Ds because that is the shell that the subshell's in. It's just, but it has to do with the energy. Okay. Now, I gotta go find a pen for this one. Let's talk about the Lanthanide Actinides. These Lanthanide Actinides, they are in the NF area. We didn't talk about the F because I can't draw it at all. I can't even come close. It's two clover leaves sitting on top of each other. Where N equals X minus 2. And if you will notice the black dotted line, which I'll make a little darker, this black dotted line starts in period 6. So that would be 6 minus, what are you doing to me? 6 minus 2. Ah, no. Six minus 2, or in other words, the 4 Fs. Is for that top row. Yes. Why is it minus? Because again, it has to do with where it falls. And the way our periodic table is typically drawn does not really reflect what it truly looks like. I can't, if I were to try to, let's see if I can even come close. If we were to try to draw our periodic table out, it just is that this 4F down here, it is even higher in energy than the 6S is. And so it comes in later in the process. But it's 4F because that's when the F subshell becomes available, is in principal quantum 4 until after the 6S does, because of energy. Okay, so we are going to get into the periodic table. And I am going to be moving around. Well, I'll not to, but you're going to keep in mind your table. So let's actually draw a version on the up here. That's good enough for what I want. Okay, and as I said, this was the NS where N equals X. This is the ND where N is equal to X minus 1. This is the NP where N is equal to X. So we're going to look at coming up with the electron configuration, and then I'll write it, and then I'm going to try to draw it up to a certain point. So for hydrogen, when you have hydrogen, you're going to start at the, it's like reading. You start at the top. In the US, you start at the top and read left to right and then down. We're going to start at the top with the 1, 1s. So hydrogen is atomic number 1. So it has 1 proton and it has 1 electron. That electron will be in the 1s. So we represent it as 1s1. So what this is telling you is this is the N value, the principal quantum number. This is the L value, or in other words, the subshell that it is. And then how many electrons are in that shell? So basically, folks, what we're describing here, we are saying that, oh, I almost really screwed up. We're saying you have your nucleus. And surrounding that nucleus is the first shell. And it is spherical in nature. And it is in that sphere that you're going to find your electron. Now, let's look at helium. I'm going to get myself in trouble if I'm not careful. Helium is atomic number 2. It's going to have 2 protons and 2 electrons. Reading your periodic table, it's in the first period. So our principal quantum number is 1. It's in a 1s. And helium is 1, 2, the second element. Because remember, I told you helium belonged over here with respect to electron configurations. It belongs over here. So 1s2. So what that means is you have your nucleus. And in the first S away from the nucleus, S being spherical, you have two electrons. They're just somewhere in that sphere. Let's move on to lithium. Lithium is atomic number 3, so it has 3 protons and 3 electrons. Folks, you still have to start here at the top of the periodic table with the first row. So our N is 1, so we have 1s. And counting all the way across, we have 1s1, 1s2, and we just have to reach lithium. Then you move to the second row, where your principal quantum number is equal to the period number, so it's 2s. And lithium is the first element in that row, so 2s1. Folks, if you will notice, if you add up the superscripts, they're always full number of electrons. Now this is where drawing gets more tedious. What it means, again, have your nucleus for lithium. You have the 1s, so the first shell away from the nucleus is spherical, and you will find 2 electrons in there. But then now we have moved on and we have a second spherical, because again it is S shell. And in this one, you have 1 electron. So that's what I told you, that the electron configurations tell you how far away from the nucleus the electron is. In the case of lithium, its outermost electron is in the second layer away from the nucleus. Lithium is more, it is our first metal. And if we were to go to sodium, its outer electron would be in the third layer away from the nucleus. And they just keep growing. I'm going to skip a couple actually. And we're going to go play with carbon. Y'all, carbon is on the periodic table, so it's going to have 6 protons and 6 electrons. Start at the top. 1s. And there are 2 elements. Reading to the next layer, 2. So it's 2s. And there are 2 elements. reading all the way across, 2. So it's 2p. And our carbon is the second element in the 2p's. Again, 2 plus 2 plus 2 is 6. That's how many electrons we should have too. This is the last time I'm going to draw, because basically if you get past this, it gets too complicated. But I want to show you how the P's come into play, if I can. I'm going to draw this one big so that they're not sitting on top of each other. So just be forewarned. It's much smaller than it is, but okay. So according to what we just did, you have your carbon nucleus in the first shell away from the nucleus, which is a spherical shell. You're going to have 2 electrons. Now, in the second shell away from the nucleus, you also will have 2 electrons. So how does the P come in? I am going to use purple to represent my P's. So also in this second layer, you're going to have 3 P orbitals. And according to what we just determined, we would have 2 electrons. Whoops, I didn't get it all the way fixed. 2 electrons, 1 in each 2 p's. That's how the electrons start to fill in. So as you can see, if I tried to draw things, it's going to get crazy rather quickly, especially since I'm not an artist. But this is what's happening is as you add on a shell, you add 2s8. So they're all and no, all in P you would discuss in new or on. You would put 1 when you get to the P. You put 1 in each orbital. So 1 is 1, 1 is 1, and 1 is 1 before pair up. But past that, no. Right now, it doesn't matter. Questions? I'm trying to give you a sense of what it looks like. But again, my drawings are not the best. Okay, so let's get out of this and we're going to start getting into, we'll get a little bit more complicated, but I'm not going to keep drawing anymore. Let me give you a moment and see how you do when you are given magnesium. And no, you are not going to have to draw either on the test. I'm not going to try to interpret drawings. How'd it go? It's 1s2, starting from the top, 2s2, 2p6, because there are 6 atoms across, or 6 elements across that section, and 3s, and magnesium's second element, so 3s2. And if you add it all up, you get 2 plus 6 plus 2, and that does equal 12. Okay, we're going to do one more, and I will tell you this, after we leave today, you're going to have to give me about 10 minutes before you open the homework, because there are some questions that we didn't go over today, so I've got to delete those before you start the homework. I want us to do titanium. Element number 22. I'm not done. I'm just getting you through to magnesium, which we just did. So. Hopefully you got 1s2, 2s2, 2p6, 3s2, 3p6, because we had to go through all of 3. Then it should be 4s2, 3d2. So it is in period 4. 4 minus 1 is 3, so it should be the 3ds. That's why I wanted to do that one, because I catch somebody all the time. You got to remember, this is 1 less than the period number for the transitions. Okay, with that, I will go in and edit the homework, and then I will see you on Monday.
I've got a quick question.
Yes.
So
Yeah, I forgot to do it today.
okay, I just saw that
No, I forgot to do it today, so everybody's going to get credit because it's my fault. It happens.